Now let's start with the first topic in CP2, recursive search and backtracking. This is a very useful and important topic. Let's study them through some examples. We are going to cover 6 example problems. Start with relatively simple ones until going to the classic recursive search and backtracking problem of n queens. So let's look at the first problem. This is a LeetCode problem called the combinations. So you are given 2 integers n and k, and you are asked to return all possible combinations of k numbers out of 1 through n. So for example, if n is 4, k is 2, this asks you to return all the 4 choose 2, which equals 6, all the 6 ways of combining choosing 2 numbers out of the 4 numbers. So here is these are the 4 numbers in some arbitrary order. So this is the solution in Java, and before you go on, I encourage you to try to solve this problem yourself. So here the solution uses the recursive search, and these slides only have the recursive part. So the sort of the main part, which call the recursive function to start the process, is not included here. So we have some global variables which are used when the recursive method will call itself and itself again and again. So this is what recursive means. So all those recursive call to this function, REC, will need to use these shared global variables. So there's n, there's k, which are the global parameters. We are doing n choose k, choosing k numbers out of from 1 through n. And we also have an array that stores the partial combination. So the recursive call is essentially gradually building up this partial combination. And when it reaches k numbers, when the array already has k numbers, then we find one combination. Then we store that, and then we go on to look for the next one. And this RES stands for result. So this is the variable that will store all the combinations. So every time we find a new combination, we will add it to here. So the recursive call, there are 2 variables that sort of changes with every new recursive call. So all the variables above here, they are shared by all the recursive call. The variable that are specific to each recursive call is I and j. Here the meaning is I is the next number to be considered, and j means that we already have j numbers added to the partial combination. So we're essentially starting from 1, we'll consider every number and consider the case of including that number and not including number until we have find the k numbers, and then we will add that as one of the combinations we are looking for. So when we write recursive call, a good habit is always have the base case at the beginning. So this is when this recursive call will return, will not call itself again. So here the ending condition is when j equals k, because this means that we already have k numbers. So we are looking for k number, we already have k number. So we find one combination, so we need to add that into the solution. So we do that by create a new array list and then copy everything in A into this array list, and then we add this array list to the result. After that base case is the general recursive case. So for every number I, there are 2 cases. We either use it or we don't. So when we use it, then we will add I to AJ, because AJ is the next the next number to be assigned, because A stores a partial combination. So if we already have j numbers, then that means A0 through aj minus 1 already occupied. We assign I to aj, and then when we do recursive call, we will be considering I plus 1, and at this point we already added j plus 1 numbers. So this is the case of using I. And we also have a case of not using I, in which case we will call I plus 1 will still have j, because at this point we have not used the I for the j plus 1's number, so we still only have j numbers remains. So we have these two cases. Now I have a question. This line have this condition which checks if n minus I is a remaining number of numbers we have not considered, right? So right now we're considering I, next time we're considering I plus 1. So we have I plus 1 through n, these numbers have not been considered. So if that number is greater than or equal to k minus j, is how many number we still need to add. Because we want k and we already have j, so only when we have enough number remains, we will call this recursive call. Because right now we are skipping I, but maybe skipping I would mean that we cannot. Skipping I would mean that we cannot find enough number to construct the combination. So in that case, we don't even call this. So the question is, can we replace this, remove this if condition, and just have this recursive calls here? I assume that you have thought about the problem, whether we can remove this if condition. So the answer is that we do need this condition. If we don't have this condition, we will run into infinite recursion. So we'll basically run out of a stack space. And the reason is if we don't have this, then we need another ending condition. So right now the ending condition is only we have selected k numbers, but because we can skip numbers, so it could be that we keep considering bigger and bigger numbers, and we never selected k numbers. So then that branch will keep go on forever. So if we do not have this check, we need another ending condition, which is well, actually, I will let you think about how would you need, what kind of ending condition would you construct, and where does it go? Suppose that here we have to remove this line. We're not allowed to have this if part. So what condition do we add in order to avoid infinite loop? But having this result in faster execution compared with sort of reaching the end, because it's prune away some of the search space, so that it doesn't consider situations where, so basically suppose you are trying to find say 10 numbers out of 20, then when you only have say you've chosen 2 numbers, and if you only have 8 numbers left, then the only choice is just to use all the 8 numbers that are left. So there's no point in exploring the search space where you skip one of the 8 numbers, because then you won't have enough number in the end. So having the check here discover that situation earlier, so it will make it faster. So when I submit 2 versions of the code on LeetCode, so this version takes 2 milliseconds, and the other version, which will return only when it reaches the end, takes 8 milliseconds. So this is the second part of the Java solution. So this is sort of the main function for this particular problem. It first assign n and k into the class variable here. And it creates the array, and then create the array list, and then you just call the recursive call, start at 1 and 0. So starting with considering number 1, and at this point we have added 0 numbers to the combination. The idea for solving this problem has been called decrease and conquer. So the idea is, in order to solve a problem of a bigger size n, you decrease n and then solve the problem for a smaller size first, and then you use that to solve the size for the size you want to solve. So in oftentimes you decrease n by a constant. For example, decrease n by 1, which is the case for this problem. So here there are two parameters, the set of number to consider, and also how many more number we need. So in this recursive call, we are decreasing both. So we are decreasing so that the set of number remain to consider, it become one less. So starting from I minus 1 to n, and the set of number the number of numbers we need to add to the combination is also one less. And the other recursive call, we are only changing one dimension. We are only changing decrease by 1 the size of the remaining number to be considered. So then in some other algorithms, we will decrease n by a sort of constant factor. So for example, divide n by 2, which is the case in binary search, and and also constructing binary tree or other divide conquer algorithms. So the idea is this algorithm for solving such a problem is if n is small enough to be solved directly, then we just solve it directly. Otherwise, we will solve an instance of a smaller size, which will be solved using the same recursive algorithm, and then we will use that solution to construct the solution to the original problem. So we use the solution to the smaller size instance to construct solution to the original problem. This is also known as the inductive or incremental approach, and this is also essentially what mathematical induction works. So there is a base case, and then proof of n is reduced to proving of a smaller n. And these can be implemented either iteratively or recursively. And for many cases, recursive implementation is the easier one to do. So, and that's what we are using in our code. And this idea of using recursion and combining a solution to smaller problem size is also the key idea behind dynamic programming, which will be covered later. So essentially, the idea when using this approach is, given the problem of size n, you sort of assume you already solved the problem of a smaller size, and then see whether you can figure out how to use that to construct solution to size n. And oftentimes this will mean you need to solve somewhat different problems or construct more information for a smaller size instance, so that you can actually construct the solution to size n. So your so that concept will be revisited when we encounter dynamic programming. So this slide gives the solution code for combinations in C++. In order to have a more succinct code, oftentimes I redefine the vector of int, which is essentially array list of integer in Java as vi, and vector of int as vvi. So this is 2D integer array. So again, so here we use a vector of integer to store the solution, the partial solution. So construct the combination we are trying to construct, and this 2D array is used to construct the result to be returned, which consists of the vector of all the combinations. And so this is the base case. In C++, we simply add this vector of a solution into this vector of int. So it is, as you can see here, it's one line. It's one line and fairly straightforward to add this vector of int into this vector of int. And in Java, as we've seen earlier, the Java code is actually 3 lines. It's quite more verbose. And I think there may be one way to do it using the new streaming API in OneLine, but I don't really like that. But it's I think for competitive programming, C++ is a better language, and this line sort of illustrate that. You can do a lot of these things in very natural code, which somehow the most natural solution, most natural code in Java actually doesn't quite do what you think it should do. So then everything else is fairly similar to the code that we do in the Java. And here, because I'm using this vector, so I use this push. Each time I add the element to the add, when I want to use J, I add it to the vector, and then when I'm done, I will remove that. So this this remove is not explicit in the Java version because I use the array and I keep an index of the array. So because when the function returns this J, the index doesn't change. So then I don't need to explicitly sort of remove that. The next time the recursive call will simply overwrite the integer. So if I change this vector with or if I use this vector as an array instead of using push by pop, I can directly do assignment, say answer J equals something, then I don't need I don't need pop back as well. So I'm just trying to illustrate different ways of doing similar things. And I think also here the recursive recursive state value, I also make it different. Here, instead of recording how many number we have stored, here I just use how many more number that are needed. So either way is equivalent.